Welcome to Statics and Strength of Materials, Lecture 6. We'll be discussing how to develop free body diagrams and perform equilibrium. A free body diagram, what is it? It serves to focus attention on the object you're interested in analyzing, and it helps you identify what forces are acting on it, which is later used to determine and to solve problems using equilibrium equations. What is a free body diagram? It is a drawing of an object and external forces on it. Nothing other than that particular object will be included, and the drawing only shows, basically has been isolated and freed from all its surroundings. As an example, I have two boxes, and these boxes are attached by a cable that goes from D to C, and this box is attached to this box by a cable that goes between B and A. If I want to do a free body diagram of the bottom box, I will draw a dashed line on that box and isolate it. And what I have there, I have the weight of that box, and then I have the tension that's acting on that box along the cable. And so that's TAB, this tension force here. If I want to look at the what's going on here, it's a good idea to include a coordinate system for analyzing these kinds of problems. Let's draw a free body diagram for the top box. So here I'll draw a dashed line, and what I see here is that I have a tension on that cable at the very top, and I have a tension at the very bottom on that cable, and I have the weight of that box. So this one, in this example, we have isolated that box along with part of the cable to illustrate the various forces acting on it. That will allow me subsequently to solve various problems in statics and strength of materials. So drawing a free body diagram, what does it involve? It identifies, you want to identify the object you want to isolate, and the choice is typically dictated by particular forces you want to determine. You want to be smart about how you want to isolate it. You don't have to isolate everything. It depends what you're trying to solve. So it's important to apply critical thinking and kind of pause. Don't just start analyzing the problem without looking at what was being asked. Spend some time understanding what is being asked and see if you can approach it. You can then draw a sketch of that object which has been isolated from its surrounding, and then you can show all the relevant dimensions and angles that you may need to use to solve that particular problem. You want the drawing to be accurate, but just remove any details that are not important. When I say that you want the drawing to be reasonably accurate, I think it's important to also have the proper scales and if you have a car that you're drawing, don't draw the tires bigger than the car because that's not just you want something that's properly scaled relative to each other, each of the other components. Draw vectors representing all the external forces acting on the isolated object, and then you want to label them. And don't forget to include weight or the gravitational force, because in many cases that drives the problem. The best way to illustrate this is through various examples. So here I have a system, and this system has been supported in the following manner. I have this sphere that has a weight of some kind, and then I also have a cable, and this cable is supported by a spring that's attached to this wall, and then I have a knot here, and this knot continues to be attached now by a cable that is attached by a pulley system at the top, and then on the left is attached by a hook. So you can see here is a fairly complicated system, and the question being asked here is, can you draw a free body diagram of the sphere? The chord and the knot. So we want to draw one for the sphere now. So let's do that. I'll isolate the sphere, draw it by itself, and then I look at what's acting on that sphere. I have a tension loads that's acting from that cable, CE. So I'll apply a force FCE in that direction because it's in tension. And then I have the weight or gravity of the sphere. I know the mass of that sphere, 6 kilograms, so I can then multiply by 9.81 meters per second squared to get 15.9 newtons. So I have that weight, that force, and that's basically my free body diagram for this particular sphere. Now I want to look at chord C, this particular chord C, and I want to look at what's acting on this chord. In this chord, if I were to do a cut, I'll find I do a cut right here and then right here, just above the sphere and just below the knot. I have a basically part of the chord, and I have the force FCE acting on from the force of the sphere acting on the chord, and then I have FEC for the force of the knot acting on the chord CE. So that's a very simple free body diagram for this particular point. Now, it's obvious that since I only have two forces and they're in the opposite direction, that they should be equal in magnitude. Next, I want to shift my attention to this knot. This knot is slightly a little more complicated, but not too hard. If I draw a free body diagram, isolating this knot, I can see what's attached to it. I have the spring, this part of this cable, and then part of this cable. So then I can now draw it and have the force acting on that knot from that cable, on that knot of this cord. Then I have the force of the spring, and I have the force of the cord acting on the knot, the one here. It's important to include any dimensions you have, any labelings you may need for subsequent calculations. In this example, we're illustrating the vertical force to a pedal, and it basically shows how a pedal actually works. In fact, the pedal is here. When you apply the load, it applies a brake to the tire, to the wheel. In this case, F represents that force. This is the mechanism that's attached to the pin. You have a spring here, and then you have this linkage. The question being asked is, the operator applies a vertical force to this pedal so that this spring here is stretched by 1.5 inches. And then the force in the short link is about 20 pounds. And so the question is, draw a free body diagram of this foot lever. And so to approach it, I have this lever being drawn. This is what I'm interested in, this lever right here. So this is your lever. And then any boundary conditions applied to that lever should be removed. So I have this pin attached to this lever. I remove the pin, and what should be reacting that pin is two loads, AY and AX. I don't know them, but we do know there are some loads that could be replaced in this pin. I also have the force applied due to the operator applying the brake, and then I have the 20 pounds from the linkage that was discussed over here, the short link here. Then I also have the spring. This spring I know applies 30 pounds. How do I know that? The spring constant is 20 pounds per inch. It got stretched by 1.5, so 1.5 inch times 20 pounds per inch gives me a total of 30 pounds force. So these are the two forces that are getting applied to this linkage, and then you have this pin replaced by the reaction forces, and then the force F applied by the operator. This concludes your free body diagram. It's important to transfer any information that such as dimensions, labels that you may later need. In this next example, I have two smooth pipes, each having a mass of 300 kilograms, and they're supported by the fork tines of the tractor. this time right here. We want to draw the free body diagram for each of these pipes and then both of these pipes together. So to solve this problem, notice that we're given masses, so clearly we should include weights associated with um, each of these times, pipes. So for pipe A, I have pipe A. Pipe A is in contact with pipe B. So clearly, I have a normal force that's acting on pipe A that comes from the contact between this pipe B and pipe A. So I should replace it with a reaction, a contact force R. I know the angle of 30 degrees, so I should transfer that information to this diagram in case I need it later on. For pipe A is also in contact to the bottom surface here, and so I should replace the bottom surface with a contact force F. That's the fork acting on this pipe A. And I also want to transfer any angle information that could be useful, and that angle is about 30 degrees to the vertical. That can be seen because this angle here is 30, so this angle also should be 30. I also have the fact that this pipe weighs 300 pounds, okay, kilograms. So I should apply that in the centroid, which is the center of this pipe, and 300 times 9.81 meters per second squared will give me 2,943 newtons. That's your weight right here. And then finally, the other force that I have is a force from the slope blade that you see here acting back on pipe A. And so that force is unknown, but it is this much, T. And then again, transfer the information relative to any angles that could be useful later on in the analysis. For pipe B, it's a little bit simpler. I have the weight, which is the same as the weight for pipe A, but now this reaction R is the same reaction R that's acting on pipe B, but in the opposite direction. So I should include that in this diagram. And then I have the force from the normal contact to the fork at this point here where the pipe B comes into contact with the fork. So now that's my free body diagram for pipe B. If I want to determine a free body diagram for pipe A and B together, I don't, now all I have here is the force acting contact on that fork blade, the weight of each of these pipes, and the forces from the contact against the fork. And that'll be it, because now this is a free body diagram for the pipe A and B together as a system. So this example actually illustrates that it's possible to determine a free body diagram for each of the pipes separately, but we also can draw a free body diagram of these pipes together. In this example 4, I want to sketch a free body diagram for this truck with the two cables who are now also being, well, the truck has a box, but this box is getting lifted from the truck. So the truck is basically not really part of this picture. It's really the two operators pulling on this cable through a pulley system, which then pulls the box or the crane up. So what are the forces that I'm interested? So I want to understand the free body diagram of point A. So I have the tension on the cable along AB, TAB. I should put the angle in there, transfer that information. I have the force TAC, which is this angle here, 30 degrees. And then finally, I have the weight of this crane, 736 newtons. And so this concludes my free body diagram for the problem being talked about. To solve problems in statics and mechanics of materials, we can apply equilibrium, force equilibrium, which can be derived from Newton's law. The equilibrium of an object under the action of multiple forces can be determined. The summation of forces equals ma, but here I have used force vector. Uh, that can be also looked at component basis. So I have summation of forces in the x direction alone, in the y direction alone, and the z direction alone. You can do it multiple ways, but in general, these are the steps you'll be using. Because force equals ma, if there's no acceleration, the body could be either in stationary, so it's not moving at all, or it has a constant velocity. And then what you have to do next is to solve for any unknown forces that you're trying to solve for. And F equals ma comes from Newton's first law. If the resultant force on a particle is zero, the particle will remain at rest or will continue at constant speed in a straight line. So that's really where these formulas come from. So here's a force equilibrium example one. I have a ship unloading operation situation. I have an auto that has 3,500 pound Newton weight and is supported by this cable system. A rope is tied to the cable and pulled to the center to the intended position. And the question is, what is the tension of this rope? So to solve this problem, what we want to do is to construct a free body diagram for the particle at the junction of the rope and the cable. So this junction here, we want to really understand a free body diagram for that area. Then we want to apply the conditions for equilibrium and solve the problem. So here at point A, what do I have? So if I do a cut around point A, I have the tension of this cable TAB. I have the weight of the car, which gets translated to this short cable here of 3,500 newtons. And then I have a force applied by the operator, TAC. And so what I can do now is I can solve for the unknown force by basically translating the vector of 3,500 pounds in a way that can solve the problem. So I can use a law of signs. I know this vector TAB, so I can draw it right here. I have the weight here, 3,500 newtons, so I can draw it here. And then I can figure out what this vector should be to close this triangle in a closed loop. So then what do I have? I can use a sign of law or law of signs and have TAB, this magnitude divided by this angle. And this angle is 120 degrees. With that information, I make that equal to TAC. TAC is this magnitude here divided by this angle of 2 degrees. Where that comes from the 2 degrees here. And that's equal to the weight of the car, which is 3,500 newtons, divided by the sine of the 58 degrees, which is this angle here. All these angles can be found by trigonometry. And so when you solve this equation, you can solve for TAC, which gives you 144 newtons. You also know the angle for that tension force. I have another example here. In this case, I have a flow on a channel, and I have this prototype sailboat, and it's basically placed in this test channel, and has 3 cables attached to it. And they're basically using a way to align its bow on the channel center line. For a given speed, the tension in cable AB is known. It's 40 newtons. And then the force, the tension in cable AE, which is this one right here, is 60 newtons. The question is, determine the drag force exerted on the hull, so on this hull, and the tension in cable AC. So if the flow is going in this direction, the question is which way is the drag going? So we're going to be looking at that. But we want to draw a free body diagram. You can choose the hull as your free body diagram. And then we can use the equilibrium equations. And we're going to use a vector this time to solve this problem. So at point A, I'll draw a free body diagram. I'll cut this area here. The flow against the hull basically provides a drag in this direction, FD. Okay. Drag is usually acting in the direction of the flow when you look at it from the point of view of the body. This cable here is TAC, this tension force here, and then this tension is 40 newtons, and this tension here is 60 newtons. So now it's simply a matter of finding these angles, which can be found through simple trigonometry because all the dimensions are given. So for example, this is 7 meters, this is 4 meters. So this angle alpha is the tangent alpha equals 7 divided by 4. So you can solve for alpha, which is 60.25, and you can put that back into this picture. And then here you can quickly find this angle as well. This angle here is tangent beta, which is this distance of 1.5 meters divided by this height of 4 meters. That gives you a beta of 20.56 degrees right here. With that information, I think I'm ready now to express the condition of equilibrium for the hull. I have the summation of all these 4 vectors here. The summation of all these forces should be equal to 0. And so now, all I have to do then is decompose each of these forces. I can decompose TAC onto the y-axis, the x-axis. I can decompose this 40 Newton load that's at an angle into the y and x-axis. And once I do that, I can then put it in vector notation. So TAB as an example is 40, so TAB is 40 newtons. So this 40 newtons right here can be decomposed into the x-axis. So if this angle is 60.26, then this load of 40 newtons can be now projected into the x-axis, and that'll be 40 newtons sine of 60.26. I hat is negative because it's acting in the negative orientation to the x direction, plus 40 newtons projected onto the y-axis, 40 newtons times the cosine of 60.26 j hat. And when I resolve this, I get minus 34.73 newtons I hat plus 19.84 newtons j hat. I can now look at TAC. TAC can be projected into the x-axis and the y-axis. So TAC times the sine of 20.56 I hat projects it into the x-axis, plus TAC times the cosine of this angle gives you the projection of that to the y-axis. And then finally I have FD, which is a drag in the I direction, x-axis, and then T hat, which is minus 60 newtons, pointed downwards, so that's why I have a J hat there. And all I have to do is sum all the forces and equal to 0, set them equal to 0. So what I get now is all these components added up with all the ones that I had have been added up, and so I get this coefficient plus this coefficient times J hat. And so now each of these coefficients must be equal to 0. So I can solve the bottom one equal to 0 for TAC, and then plug it back into this coefficient, which also has to be equal to 0 to solve for the drag force. That's exactly what we have done. You can also solve the problem by summation of forces in the x direction, solve for summation forces in the y direction, solve for TAC, plug it here, and then get the drag force as required. There's yet another example. Here I have a weight of 396 pound force I have these cables that are attached to a pole, and the question is, what is the tension in these cables? Again, I'll draw a free body diagram around point C. And I know all the slopes, so it's again trigonometry. I can take each of these tension loads and I can project them to y and x axis. TAC can also be projected into the y and x axis, and I can sum all the forces in x directions, all the forces in the y direction. And when I do that, here in the first equation, I can find a relationship between TAC and TBC. In the second equation here, which is the summation of forces in the y direction, I can basically, I have a second equation here. I can plug in TBC into this equation and solve for TBC. And once I have TBC, I can solve for TAC. So it's two equations, two unknowns. It's a simple equations to solve for TAC and TBC. Example 4 is a little more complex. It deals with collars A and B. These collars A and B are connected by a 25-inch long wire. This wire can slide freely, and how it can slide. So these are frictionless rod that can slide. So these collars can slide along these rods, and this collar can slide along this rod. This is a very interesting problem because the question here is, if I were to apply 60 pounds along the z-axis to this collar, the question is, what is the tension in this wire when the distance between the collar and the y-axis is 9 inches? And then the second question is, what is the magnitude of the load P that needs to be applied to maintain the system in equilibrium? This is an extremely interesting problem because it requires looking at various free body diagrams. So what I'm going to do first, the strategy is to draw a free body diagram of the particle. This diagram shows the particle and all the forces acting on it. And so then we will then set the resultant, or the sum of forces, on the particle equal to 0. That will be the strategy that we're going to be using. The first step is to find a unit vector connecting A to B. What is a unit vector? So to do that is very simple. I can find the vector that connects A to B because I know the coordinates of this point and the coordinates of this point. If I were to leave x as an arbitrary number and z as an arbitrary number, you should be able to find this vector AB. And so once I find it based on the coordinates, which are minus xi hat minus 20j hat plus zk hat, I want to divide that by the length of that wire. I know the wire is 25 inches. So this is almost like a constraint, but I know that this is my unit vector. This is my unit vector right here. So then I want to draw a free body diagram of collar A. That's my first step. Collar A is along this rod, frictionless rod. So therefore, the rod is imparting contact forces onto the collar in two directions, potentially in the vertical directions and also along the z direction. So therefore, I'm going to put in here NYJ hat in this direction and NZK hat in this direction. In addition, I have the tension in this cable, TAB, but I want to know the vector, and I want to put in vector notation. But since I know the unit vector, which was calculated through this procedure, then I have TAB times lambda AB. And finally, I have a load applied in the P direction, in the X direction, a load P applied on that collar. So it's P times I hat. So then I'll sum forces of all these forces, force vectors, and set them equal to 0. And so what I'm going to do next is to substitute for lambda AB and set all the coefficients of I equal to 0. If you note here, I have lambda AB, which has I and j and k hats. When I plug this into this equation, TAB times x is going to have a I hat, and this P has an I hat. So that coefficient has to be equal to 0. And so I end up with P minus TAB times x divided by 25 is equal to 0. The free body diagram for color B can now be determined. If I look back, I have a force applied of 60 newtons in this direction. I have the wire, in, attention that wire, and then I have the normal forces keeping this rod, this collar from getting removed from that frictionless rod. So then I have normal forces acting on this collar. I have the traction or the tension force acting along the wire, and then I have this Q vector. Again, I'll sum forces in the x, y, and z direction, or just simply add the vectors together and set that equal to 0. When I do that, I realize that if you look here, I have 60 pounds k hat. If you go up here, lambda has a k hat, z divided by 25. And so what's going to end up happening is that the only thing that's going to have k hats is that coefficient of 60 and TAB divided by 25 times z. And so that's what you end up getting there. You can solve now. You know what z is, by the way, because you can use the distance between these 2 points. The distance between these 2 points is 25. So I have 9 squared, because this distance is 9, so 9 squared, 20 inch squared, which is the height of that point relative to this point, and then z squared, which is the distance between this point and where the collar is. I know that has to be 25 because the length of the wire is 25, so I can solve for z. Z is 12. Once I know what z is, I can plug it in here, get the tension on the wire, which is 125 pounds. And once I know the tension in that wire, I can go back here, plug it in here. I know what x is 9. It was given to us. I can find the load P to maintain the system in equilibrium. We're going to determine the tension in the cables BA and BC to support this 60 kilogram cylinder. Again, I'm going to draw a free body diagram of this cylinder. What do I have? I have the weight of the cylinder, and then I have the tension on that cable, BD. So I know the 60 kilograms. I know the acceleration of the gravity, 9.81, so I can now determine the weight. And since I know this tension on the cable is unknown, this has to be equal and opposite to that weight. There's no other choice there, right? And then once I have this one, I don't know TA and TC, but I could determine that by simply summation forces in the x direction and summation forces in the y direction. For example, this TC, and again, this is a free body diagram of a rod around this ring B. So I do a cut there, cut here, cut there. And so what's acting there, tension in that cable, a tension in this cable, and then the tension in this cable. I know how much this tension is, and so I want to find TA and TC. So simply what I have to do, I have to resolve TC into the x and y directions. TC of cosine 45 puts in the x direction, and then I can resolve TA in the x direction as well, and that will be basically 4 divided by 5 times TA. That gives me the component of TA in the x direction, because we're projecting TA onto the x direction. And then I can do the same thing and project T into the y direction, which is can be easily done. And then I can, which would be 3 over 5 times TA, and then TC can be projected into the y direction and x direction. That would be, in the y direction would be TC times the sine of 45, And then I have in the vertical direction, I have the 60 times 9.81. If I sum forces in the x direction, but to the right, so everything on the right is positive, then I can set this equal to 0. If I sum forces y in positive moving up as a convention, if it's moving down, doesn't matter, you will still get the same answer. This is the equation I get. I have two equations, two unknowns. TA and TC are unknowns. Two equations. I can solve equation 1, TA as a function of TC. Substitute TA as a function of TC into the second equation, solve for TC, and once I solve for TC, I get TA automatically. So these are the two tensions that I get. I know their directions, so these are very well-defined problem. Here's a car that's in an inclined ramp. It's supported by a horizontal cable, AB. The car brakes are not engaged, so the tires exert only a normal force on the ramp. And so the question is, determine the magnitude of the force exerted on the car by this cable. So I draw the car by itself. I draw the weight of the car, and I apply the normal force to the car, which is, those are the only forces that we have in addition to the tension force of the cable. So I have the weight of the car, the normal force onto the car, which is inclined at 20 degrees, and I know that because this angle is 20 degrees. From trigonometry, you know that's also oriented at 20 degrees. Again, I can sum forces in x direction, so I have tension in the x direction, minus, and then I have this normal force N, which can be resolved in the x direction. And so that'll be the N times sine 20 degrees. So I have T minus N times sine 20 degrees, equate that to 0, and then in the y direction, I have the N, again, N times cosine of 20 degrees, and the weight of the vehicle in the opposite direction, that's equal to 0. Again, I know the weight, I can solve for N. Once I know N, I can solve for T. So it's a fairly straightforward problem. Here's yet another example, is an mobile engine block. It's suspended by a system of cables. The mass of the block is 200 kilograms. The system is in equilibrium. What are the tensions in cables A, B, and AC? Same process. This is the engine block. I'm going to draw a free body diagram around point A. Why? Because this weight of this engine is known, so it will get transferred to this cable. So it just makes sense to just do a cut right here, right there, and right there, and then draw a free body diagram. So I have the cable TAC, TAB, that tension, and then the weight here. Then I can decompose TAB into the X and Y components, TAC into the X and Y components using simple trigonometry, as we've done over and over and over. This is the weight W. So anything that's added in the Y direction, these vectors added in the Y direction should be equal to 0. These two vectors added in the X direction should be equal to 0. So that's what I have here, the first equation, and then I can write the second equation. Two unknowns, TAC and then TAB. So I can solve for TAC in terms of TAB, plug it into the second equation, and then solve for TAB. Sorry about that. And then I can find the cable tensions to maintain the system stationary and in equilibrium. And so in this example, what we've seen is that is very simple. So here we have the example of a pulley of the system. The mass of the suspended object is A. The mass of each of these pulleys is M. And so what we want to determine is how much force I need to apply to this cable to maintain the body in equilibrium. So everything's either stationary or moving at constant speed. So what I want to do, the strategy here is to do a free body diagram for pulley B. So cut here, cut there and cut here. I can do one for D, cut here, sorry, cut here, cut there. You can also cut at the very top, cut here, and then a tension force applied. So let's see how to approach it. The first step is to do a free body diagram of C, this pulley system C. So I have C here, this pulley system C. There's a load applied on a cable that's acting on the pulley system. That's TD, I'll call it. And then this force tension T that's applied gets translated through the pulley system to the other side, and that should be equal in value. In this case, they're acting in the same direction. That makes sense. I can solve for TD. That will give me 2T plus mg because I have TD has to be equal to 2T plus mg to balance the forces in the x direction for that pulley system. Then I can do another free body diagram on B, and here I have a number of forces. I have this tension here of this cable that goes to the other side. That tension has to be the same still. So this tension is T right there, and then on the other side around the pulley, that tension is also T. TD was found to be 2T plus mg, and that's also acting on this cut right here, equal and opposite. So I have this. I know the mass of that object, which is AMA times G, and I know the mass of the pulley system, which is mg. So all I have to do now is add all the forces in the y direction. There's no forces in the x direction, so that should be a fairly simple task. Again, I know all these masses, so I'll have 4T plus mg minus mg minus mag, and that'll have to be equal to 0. So I should be able to solve for that tension now. So here it is. When you solve it, you get mag divided by 4 to make it happen, to maintain this body in equilibrium. The next example, final example, is an airplane. This airplane has a flight path x at an angle of attack alpha. Angle of attack alpha, you have the thrust vector, which is acting along the plane axis of the vehicle, the lift, which is acting in perpendicular to the angle of attack on the x-axis. This is your path of flight. So the lift always acts perpendicular to path of flight. You have the drag that acts opposite to the movement of the aircraft along the path of flight, but it resists the motion, so that's why it's in this direction. And then I have the weight of the aircraft. So one more time, you have the thrust, which is usually along the axis of the aircraft. You have the flight path, which is at an angle of attack, and the lift always acts perpendicular to the flight path. And so we should be able to now determine what values of thrust and angle of attack alpha are meant. This angle here, sorry, thrust, is required to maintain a steady flight. So in terms of the coordinate system in the figure, we can write the equilibrium equation. So let's look. So I can resolve T into the x-axis. That will be T cosine alpha along the x-axis. This W can be resolved into the x-axis as well. And you know this angle, so you should be able to determine what weight component goes into the x direction. And that weight here will be the sine of gamma. This sine of gamma here is the angle that should be used in the calculation here. And so in the x direction, I get T cosine alpha minus the drag minus W sine gamma equal to 0. In the y direction, where the lift has been aligned with the y direction to make it easier for the calculations, this time I have the W of cosine gamma instead. And I have this thrust vector, which should also be looked at. This thrust vector also is WT sine alpha when you resolve into the y direction. And so those are the only forces applied. And so now the airplane weight is known. It's 72,000 kilograms. Acceleration due to the mass is 72,000 kilogram. The acceleration due to gravity is 9.81. So you know the weight. So if you know the weight, we should be able to solve this equation right here for sine of alpha, because weight was given, lift was given. You can see here, lift is given in the problem statement, okay, and the drag is given too. Weight is given, lift is given. So now you can solve equation 2 for sine of alpha, solve equation for 1 for cosine alpha, and divide the two equations to find the tangent of alpha. Little trick, gamma is known, the weight is given, lift and drag are known, so I can get the tangent of alpha as 0.113. Then your angle of attack will then become 6.44 degrees. Now we can determine the thrust. The thrust can be quickly determined. If I have alpha and I know the lift and I know the weight and I know gamma, I should be able to find thrust. And so that's exactly what was done. And the answer is I have 200,000 kilonewton thrust that needs to be applied with an angle of attack of 6.44 to get a thrust for steady state flight. Note that we need to apply about 28% of the airplane's weight to make this work.